So today we'll be using Kerbal Space Program and a little bit of math to explain how orbits work and how we build rockets to get there. So I'm just going to load up this rocket I have here, and I'm going to set it up to launch right now. This will be a really simple demo, and if you already know how to play Kerbal Space Program, uh, this will be quite redundant for you, but I still hope that you can find it entertaining and perhaps maybe learn something new from it that you didn't before. But for today, we have one simple goal, and that goal is to get to orbit. Let's find out if we do it. So what we have right here is a very small rocket, and some astute observers might say that it's not going to make it to orbit. Well, we're draining fuel pretty quickly here. We're almost at a quarter tank, as you can see in the bottom left-hand corner. So you're probably right in that assumption that we're not going to make it to orbit initially. But this is for the purpose of demonstrating what it takes to get to orbit, so just hang in with me a bit there. So for our first rocket design, we are using a solid rocket motor as our main engine for the rocket. There are two types of rocket engines, solid rocket motors and liquid-fueled motors. Most rockets today for human spaceflight use liquid-fueled. So why are we using a solid rocket motor? Well, there's many pros and cons associated with that, and we just had a engine cutout, but we are going to continue to drift for quite a bit. But there's many pros and cons to using a solid rocket motor. One of them is that you can store the propellant on that rocket for a very, very long time without much propellant degradation. And they always launch reliably because of that. And for this reason, they're actually used a lot in military applications like missiles when you want a rocket to always go off. And there's not a lot of moving components associated with it. There's fuel on the inside and a nozzle. And it gets a little bit more complicated when you add thrust vectoring into things, but for the most part, it's a very simplistic design in comparison to the complexity of a liquid-fueled engine. However, the downside of a solid rocket motor is that you can't throttle it and you can't turn it off. Once it's lit, it's lit. There's no stopping it. And that can make these type of rockets a little more dangerous, especially in some scenarios where there's a danger to the crew. You can't just immediately turn this rocket off. But I'm going to stop talking about solid rocket motors right now and notice that we are quickly approaching space right about now. So in Kerbal Space Program, space is defined at 70,000 meters or 70 kilometers. Hearing that music indicates that we are in space. So I can switch to the map view and show that, yeah, we have made it to space, but we have one problem. We're quickly approaching the high point of this trajectory right here called the apoapsis. And once we pass that, we're going to go straight back down to where we came from. So this is a problem. We are in space, but we're not going to stay in space. So what did we do wrong? So for that, let's go to some context. So let me switch over to Team Viewer and start talking about that. So on Earth, space is defined as 130 kilometers in altitude above the surface. That's about 62 miles in freedom units. And in Kerbal Space Program, we actually go to 70 kilometers, as I mentioned earlier. But we forgot one big thing about getting to orbit, and that is that orbit is, or objects in space are, instead of flying, they're falling. So what does that mean? Well, we can go to an old excerpt from our friend Isaac Newton, And the following excerpt comes from his 1728 book, A Treatise on the System of the World, and it reads, "That by means of centripetal forces the planets may be retained in certain orbits, we may easily understand if we consider the motions of projectiles. For a stone projected by the pressure of its own weight, forced out of the rectilinear path which by the projection alone should have pursued and made to describe a curved line in the air, and through that crooked way it is at last brought down to the ground. And the greater the velocity with which it is projected, the farther it goes before it falls to earth. We may therefore suppose the velocity to be so increased that it would describe an arc of 1, 2, 5, 10, 100, 1,000 miles before it arrived at the earth, till at last exceeding the limits of the earth, it should pass quite by without touching it." So what does Isaac Newton mean by this? Well, he's saying if we take a stone and we throw it from the top of this mountain right here, at some velocity, it will create this arc that goes around the planet. And essentially, we are falling past the horizon. We are falling past the planet or the orbital body. And if we throw it fast enough, we create this arc such that we stay there forever. And so this assumes that we are throwing a stone and it's not being affected by any sort of air resistance. But this is just a simplistic thought experiment that Isaac Newton had back in the 1700s. For a mathematical representation, what he is describing is the battle of two forces. One is the force of gravity, or F of g, and the other is the centripetal force, or the force that we have that is created by flying in, or by moving in a direction and being acted upon, or being moved around, so like similar to the centripetal force that you might feel in a car as you're going around a tight curve. So putting into more mathematical terms, and I'm going to be using some math here. It's okay if you don't immediately understand it. We're just using this as a foundation. This isn't meant to be a math class, but again, just to provide some foundational knowledge into why orbits work the way they do. So first we have the equation for centripetal force, which is going to be the mass of the object times its velocity squared divided by the radius. And then we have the force of gravity, which is equal to the gravitational constant times the mass of one object multiplied by the mass of another object, all divided by r squared. So in astromechanics, we can actually simplify this first term right here to be equal to the gravitational parameter, or mu for short. And for reference, mu of Earth, and anytime I draw a circle with a cross through it, it denotes the Earth, is equal to 3.986 times 10 to the 14th meters cubed divided by seconds squared. That is a really, really big number. But we have the benefit of using Kerbal Space Program. In Kerbal Space Program, everything is really shrunk down. It makes it easier for demonstrating things. You can get to orbit a lot quicker. You can get to orbit in about 3 minutes, as opposed to in the real world, it can take up to 10 minutes to achieve orbit. So we get to cut out a lot of the dead time. So on Kerbin, we know that the gravitational parameter is 3.532 times 10 to the 12th power meters cubed over seconds squared. And so we can substitute that equation and we can solve for this diagram right here. So I'm going to equate the force, the centripetal force, to the force of gravity and substitute. So in this case, we're going to use the mass of the second object, similar to how it is represented in the force of gravity equation, is equal to the gravitational parameter over r squared. Again, substituting out that for the gravitational parameter, we get a lot of these terms that cancel out. We can cancel out one of these r's, and what we are ultimately left with is that the gravitational parameter of Kerbin is equal to the radius of our orbit times velocity squared. And we can use this really simple equation to solve for any circular orbit around this particular orbital body. And with that, we can plug in our numbers. 3.532 times 10 to the 12th power is equal to the radius of our orbit. So if you remember, we mentioned that the space for Kerbin is at 70 kilometers. Well, we also have to take into the account the radius of Kerbin itself, which is equal to 600 kilometers. So in this case, we will use 70,000 meters plus 600,000 meters times velocity squared, where v is equal to the square root of 5.272 times 10 to the 6th power, and that all simplifies to 2,296 meters per second. So to achieve a circular orbit around Kerbin, we need to actually apply a lot of energy to get there. It's not as simple as just going straight up and hoping that we stay up there. We're actually moving at quite a speed. For reference, the circular velocity around Earth at about 300 kilometers is equal to 7,826 meters per second, or 17,500 miles per hour. That is fast. So we need to be moving at really a fast pace, and we need to design a rocket that can get us there. And we also have to worry about that little problem of atmospheric drag. So in this diagram right here, to get rid of, or to mitigate the effects of atmospheric drag, first we fly up a little bit, and then we do a pitch over maneuver until we're flying almost completely horizontally. And in this diagram, the thickest part of the atmosphere is below the dotted line. So we are trying to get through the thickest part of the atmosphere as fast as possible before we start applying that horizontal velocity. So let's do it in Kerbal Space Program. All right, so I'm going to load up another ship here called Orbiter, because this is going to be the ship that we're going to use to get to orbit. And this one has a little bit more energy in it. It's a 2-stage rocket, and it's also liquid fueled. So we'll load this up. I'm going to throttle it up and launch. So this rocket is really similar to the first rockets used to launch Americans into space back in the 1960s. And it was a modified version of the existing Redstone and Atlas missiles. So yes, our first astronauts were quite literally riding missiles into space. That's pretty cool. In 1962, John Glenn became the first American to orbit the Earth, and he rode a liquid-fueled rocket similar to this one. There are several reasons a liquid-fueled rocket was chosen to send astronauts to space. One of the major ones is it can throttle up and down, so I'm going to lower the throttle and increase the throttle. I can modify how much exhaust is coming out of this rocket, and by that factor, I have a little bit more control over it, and that provides an important factor of safety to the crew. And so we've already started to pass through the thickest part of the atmosphere, as indicated by this barometer up here. It's just a really simplistic system, so I'm going to start our pitch over maneuver. I have started it a little late, so our apoapsis might end up being a little high, but I'm currently shooting for 70 kilometers. I'm actually going to throttle down here a bit, just so that we can actually hit that, because we have gone a little further than I was expecting to. But as you can see, that's what this liquid-fueled rocket provides you the variability with. If there's things that happen during flight, you can make quick changes. So I'm actually going to do a really aggressive pitch over maneuver, and this is a pretty poor representation of how one gets to orbit. Typically, it's a much smoother curve uh, as you approach the horizontal vector, but we're doing this live. So pretty soon we're going to run out of fuel here, and I will jettison the first stage. But I will not light the second stage immediately because we have achieved enough velocity that we can now coast to our apoapsis. As I switch to the map view, we have some time it takes to get to apoapsis. Our apoapsis is going to be at 87,000 meters. And I will apply this maneuver node, and essentially what this is, it's an extra burn. It's a second burn that we're going to do at a very specific point in space so that we can circularize this orbit. So I will time warp to that point, just fast forwarding time so we don't have to wait for it to get there. Slowing things down, and I'm going to go full throttle. And so this burn is going to be a very short burn. I'm going to switch to the map view for it, and you can see we are creating a much larger orbit, and pretty soon it will make a full circle around the planet that we are in. Right, so I'm going to stop it right there. We have an apoapsis of 88,000 meters, and we have a periapsis, the lowest point in our orbit, of 82,000 meters. And with that, we have achieved orbit. And so I can just do a quick time warp to show you that, in fact, we're not going to fall back into the planet. We're just going to keep barely missing it every single time, following Newton's conjecture that if we were going sufficiently fast enough, we would just barely miss the surface and continue to fall indefinitely. And that's exactly what an orbit is. Being weightless, you aren't actually weightless in space, you're just constantly falling. And so that is what mimics that weightless factor that you would have in space. But I did something there. I did a little burn at the top of that. So let's explain what actually happened there, because that was a little quick. So right here we have the planet with a dot in the center. So this white line out here represents the surface of the planet. And then right here represents the orbit that we currently were in. And as you can see, parts of the orbit actually cross the planet itself. So this is indicating that we would crash into the planet, and this is where we started from. So we were launching, and we were trying to get to the apoapsis, or the highest point. And at this highest point, that is where we can expend an efficient amount of energy to get to a circular orbit as efficiently as possible. So that was our goal here. And we did that by burning in a prograde vector, prograde meaning the direction of travel at that current time. And we were adding more energy to the path velocity vector that we were currently at. If you were noticing, we were currently going 1,600 meters per second, and to achieve that circular orbit, we needed to be going 2,200 meters per second. So we had to make up that change, or that delta. And the best way to do that was to wait for the most optimal time to make a prograde burn. If instead we wanted to go back to the planet or make our orbit smaller, we could have burned retrograde, which is the opposite direction of travel. There are other different vectors that we can burn along in the spaceship, one of them being the normal vector and the other one being the anti-normal vector. And I'll just draw this little diagram right here. And so this vector right here is prograde. And this vector going in the opposite direction is that retrograde vector we were talking about. The normal vector is really the up direction. And this is an important vector to use for when you want to change your orbital inclination, because if you're already traveling along this path, if we add energy in the upwards direction, we actually change our direction of travel slightly, and we add this little angle here, and that angle can be referred to as inclination. This is also referred to as a orbital plane change. The last two orbital vectors that we can burn in are radial. So radial is inwards towards the planet, and anti-radial is outwards, away from the planet. And so with these 6 vectors, we have enough information right now to completely change the orbit that we're currently in. But right now we're just in a circular orbit we're going around, but we'll switch over to Kerbal Space Program to demonstrate what would happen if we were to apply those changes. So I'm just going to create another maneuver node here, and you can see we have those same 6 icons, one being the prograde vector, which changes the orbit like that. I can make another maneuver node and burn along the normal vector. And this was that plane change I was referring to. It's creating that angle between the orbit itself. And currently we launched from the equator, so we're traveling in a perfectly straight line around the planet in a curved fashion. But if we added this inclination, we start traveling. It's still in a perfect line, but or a perfect circle, but we're traveling at a slightly different angle, and there's going to be 2 points in that orbit where we cross the equator. The last type of burn would be radial. And radial we can use to modify our orbit like so, but it's typically not very fuel efficient. You can get a much better result out of instead either burning prograde or retrograde to modify your orbit. There are very rare scenarios where you would want to burn radially, mostly used in rendezvous proximity operations, or when you're docking with another spacecraft and you really need to fine-tune and line up your orbit with the other object. Because you are traveling so fast, you need to make sure that your relative velocities between the two are near zero to do an efficient and to do a safe rendezvous. So I'm just going to do a real quick burn right now at the prograde vector. And what that's going to do is it's going to increase the eccentricity of our orbit just very slightly. But if I had more delta V, I could increase the eccentricity of the orbits really, really far. So this circle right here we refer to as an ellipsoid, and all orbits are an ellipsoid. And we can go to the chart right here to describe that. And this is this comes from Kepler's 3 laws of planetary motion. Now, in Kepler's time, he made these observations based on looking at the planets, and at that time they even considered the moon partially to be a planet. But really, this should be renamed to the Kepler's 3 laws of orbital motion. Okay, so the first law of orbital motion is itself the law of orbits. And I was getting into this a little bit, where every single orbit can be described as an ellipsoid. In fact, it is an ellipsoid when we're only worried about 2 bodies interacting with each other. When you add more planets, you can get some really funky looking orbits, but this is just for a simplistic version of it. So you create an ellipsoid by having 2 foci, 2 centers of that ellipsoid, one of which being the center of mass of the object you're orbiting, another one being out in space. And so if we draw a line between these 2, we get what's called the major axis. And if we draw a line crosswise along the short part of the ellipsoid, we get the minor axis. And with that half section of the major axis, we call that the semi-major axis. And in classical orbital mechanics, we refer to that as A. And A is one of the 6 classical orbital mechanics that we use to describe an orbit, alongside eccentricity, inclination, and then 3 other little more obscure factors. But with those 6 classical orbital elements, we can define every single orbit that there is. So on the second law is the law of equal areas. And so suppose that we bisect this ellipsoid at point Q and point P, such that we describe an area A. And with the spacecraft traveling along this ellipsoid, it takes a time t to travel along that arc right there. And suppose we draw another bisection of this ellipsoid with the same area, A. So these two A's right here are equal to each other. They are the same exact values. And we just define that with Q prime and P prime. Well, what that means is the time it takes to travel along this arc right here is also t. So you can imagine this as you're traveling along, you slow down up here, and you really speed up, and you start slowing down again. And so that's what that means. And it gives us a way to describe the amount of time it takes to cross a certain portion of the orbit, and it creates a little bit of harmony in how orbits work. And then the last one we refer to as the law of harmony. And what the law of harmony is that any orbit with the same semi-major axis will also have the same orbital period. So it will take the same amount of time to travel around this orbit once as it will to travel around the other orbit once, as long as they have the same semi-major axis. This is really powerful because it allows us to take that same equation that we have for a circular orbit, and a circular orbit like here with a semi-major axis of A, and we know the amount of kinetic energy in this orbit. There's actually the same amount of kinetic energy in this orbit as long as A is the same. We might be traveling through certain sections of it a lot faster than others, but the orbital period and the amount of kinetic energy to get into that orbit is exactly the same. So we can apply a lot of simplifying assumptions when doing our orbital mechanics. So the last thing I wanted to talk to you about is how we go about building these rockets. So on the next slide, we have the Tsiolkovsky rocket equation. And this hinges upon this diagram right here. And it's the basis for how we propel rockets through space and through the atmosphere. And that's a simple equal and opposite reaction going back to Newton, where if we expel a mass out one direction, it's going to propel the other object in the opposite direction at an equal amount. So we describe the mass leaving the object as VE, or the exhaust velocity, and we describe the amount of energy added to the rocket as delta V, where the triangle is the Greek letter for delta, delta V describing the change in velocity. So with that out of the way, we can go on to the Tsiolkovsky rocket equation, which is defined as delta V equals the exhaust velocity times the natural log of the initial mass divided by the final mass. And I'm just going to turn off Kerbal Space Program, because that music can, while pleasing, can be a little annoying sometimes. So we have this equation right here, And what do we mean by the exhaust velocity? How do we go about calculating that? Well, in rocket engineering, we decompose this term to be the specific impulse times the gravity of Earth. And this is going to be applied to no matter what body you're on. If it has a different gravity, if you're in space where there is no gravity, quote unquote, uh, you're still going to apply Earth's gravity to this equation because it's just a simplification for how we can compare different types of rocket engines using specific impulse. And you can think of specific impulse similar to the fuel efficiency of your car, similar to miles per gallon. The higher your specific impulse, the more efficient you are being with your fuel. And this is also a readily available parameter and used for comparing different types of rocket engines and different types of fuel. So with that out of the way, we can take the Tsiolkovsky rocket equation and use it to calculate the amount of energy and the amount of delta V that we have in our rocket. Now, Kerbal Space Program does this for us, but it didn't always used to. But we can use this rocket as an example. So I've got two of these fuel tanks. One fuel tank is 360 units of fuel and 440 units of oxidizer. Fortunately, in Kerbal Space Program, each unit of fuel is 1/100th of a ton. So we have 8 tons total of fuel. We can look up the rocket's mass as 12.583 tons. And then finally, we can go into the engine that we're using specifically for this and get the engine specific impulse at sea level, and that is 250 seconds. So with that, we have enough information uh, to calculate how much delta V we have here. And notice that it says for this stage, we have 2,476 meters per second. So let's see if we arrive at the same number. All right, so we have our fuel. That's not how you spell fuel. Weighs 8.0 tons. Our initial mass, or the rocket total mass, is equal to 12.583 tons. And then our final mass, also referred to as our dry mass because it assumes that we drain all of the fuel from the rocket, is equal to 12.583 minus 8.0, which is equal to 4.583 tons. And our specific impulse for that engine at sea level is equal to 250 seconds. And the gravity of Earth, or G0, is 9.81 meters per second. So with that, we have all the information we need to solve this equation. So delta V for our first stage is going to be equal to 250 times 9.81 times the natural log of 12.583 divided by 4.583. And doing that really quick because I already have the answer here is 2,477 meters per second. And you'll note that Kerbal Space Program actually said it was 2,476 meters per second. There could have been a rounding error on Kerbal Space Program's part or my part, but that's the answer that we arrive at. And this is how we calculate the amount of energy in a rocket and what we use to design it for specific applications. So with all the information that we've talked about today, we can now apply it. So on the left, I have a delta V map of Kerbal Space Program, and on the right, I have a delta V map of the solar system. And the way that this is designed to work is you follow where you're starting from and try to add up the numbers of the things that you pass through. So if we wanted to go to the moon or mun, we have to add up this number right here, which is 3,400 meters per second, plus the amount of energy to intercept with the moon, which is 860 meters per second, plus 310 meters per second to get into a circular orbit on the moon. And then finally, 580 meters per second to land on the moon. So we can use this as an engineering tool to design a rocket. And in the same way, we can do that for Earth. So on Earth, it takes 9,400 meters per second to escape Earth's gravity and find yourself on a low Earth orbit. And that's really putting all of this together. And again, it's okay if you didn't quite understand all the math there, but hopefully this helped explain some concepts. And the last thing I have to show is a comparison of a rocket that would achieve orbit on Kerbin, which is the planet in Kerbal Space Program, and the rocket that will achieve orbit on Earth. You can see that it changes a whole lot when you have to have when you have a much larger planet to escape. It actually increases exponentially. So instead of just having this small rocket stage like we had for Kerbal Space Program to launch a 1-ton capsule, we have all of this supporting structure, and the rocket is essentially 99% fuel. But that's all I have for tonight. I believe, yeah, we are right on time. So if you liked hearing what I presented tonight, please let us know. Give me any comments on what you might like to see differently if we were to do topics like this again in the future.